Good afternoon, everyone, and a warm welcome to Isifundi Training. Now, in this series of Isifundi Training's Bite-Sized Corrosion, we've been digging into our collective experiences with vandalism and theft within the cathodic protection space. We've been looking at some of the challenges, trying to identify some of the hardware solutions, looking at some of the nuances of the problem, trying to see how our cathodic protection experience fits in perhaps to a bigger picture. Today, I thought we'd try and take this a little bit more technical, shall we say, and I'm delighted to welcome a very familiar face back to the mic, and that is Neil Webb from Isiniti. Neil is the technical director at Isiniti and has in excess of 40 years of designing cathodic protection systems. We could say he's probably seen it all. So thank you for joining us today, Neil, and welcome.
Hi, Vanessa.
Now, Neil, during the past few discussions with various guests, we've heard increasingly harrowing tales about how cathodic protection equipment is being vandalized. Primarily, it seems, within Southern Africa, it's being vandalized for the economic value of the components. Now, I know full well that this speaks to a socio-economic challenge, which is way outside of the expertise of most corrosion engineers. And although we may not be able to fix the underlying cause, I wondered if you could help us explore some technical approaches that we could possibly explore to reduce this risk.
Well, I think one of the approaches which we alluded to earlier on the series is out of sight, out of mind. If the cathodic protection equipment is not that visible, then it is less likely to be targeted by theft and vandalism. Of course, once people know that it's there and that there's copper to be had, copper is a highly recyclable material and therefore is a target. So one of the aspects of this is to make the equipment less copper heavy, if I can call it that. And in that regard, we heard from Cathodic in particular talking about the use of switch mode power supplies, for example, where they have reduced the copper content of the rectifiers significantly. The net result is that there's not that much return to be had for actually stealing one of these things. But of course, you can't do away with it completely. The advantage of coming up with these smaller power supplies, for example, is that you can bury them. And we've seen the fiber optic systems being rolled out across the country with these subterranean chambers. And you often see the guys sitting next to the sidewalk with a nest of cables coming out, and they're parked there doing whatever they do in terms of testing and maintenance of fiber optics. And one can adopt the same approach with cathodic protection equipment. You can make these units retractable or extractable, if you like, pull them up above ground level to service them and then put them back down again. The big challenge, of course, that we've had in the past has been heat generation.
Yes.
So when you have conventional transformer rectifiers, which are iron cored, copper windings, they generate a fair amount of heat and they're very heavy. To be able to make rectifiers that are powerful enough to run the older CP systems where you were having to push out many kilowatts of power through a conventional rectifier that may only have, say, 60 or 70% efficiency, the balance of that power is generated as heat. And where does it go to?
Yes.
So that's one thing. The other thing is, how do you make these chambers so that they don't leak?
Yeah.
Because if you're dealing with electricity, you don't want to mix it with water.
Water's not great, correct?
No, I mean, we want water in our ground beds, sure, but that's a different story. We don't want water in our power generation systems. So the manufacture of enclosures that can be buried and that are then hermetically sealed so that you can have equipment in there that is dry is a challenge. And we have recently seen some of these fiber reinforced enclosures being manufactured with differing locking systems and also seals from the top, because Whilst we want to be able to get in from the top, you don't want the rainwater to get in from the top. So it's not just a case of water seeping in through the walls or through cable glands and so on. It is actually has to be protected from the top as well. So we're seeing these systems become available, and they are hardly visible. The problem actually, though, is that people see it being installed. They know it's there.
You made a comment, Neil, a little while ago, which actually struck a thought in my mind. You mentioned that the fiber optics people, seeing them on the side of the road doing their repairs, and the fiber optics people that I've been exposed to have always had purple and green and pink colored cables. I'm wondering whether the cable manufacturers shouldn't think about changing their colors, and I mean this in all sincerity, because we expect the black and the red to be associated with copper.
Yeah.
And
Yeah.
if there were
Yeah.
different colors,
Well,
they might initially think, oh, well, this is just fiber optics, and maybe leave it alone. But yeah, you make a very valid point. You're watched while you're installing, and that kind of makes it a target before you've even closed up and left site.
it's an unfortunate fact, I think, that we often see that the theft and vandalism occurs during construction already. And once the installation contractor has left site and there's no longer activity on the line, the level of vandalism does tend to reduce. I won't say it goes away completely, it's a bit of an indictment against the installation contractors, but they are in turn almost forced to use local labor again, going back to the socio-economic aspect of things.
Although I wonder if it does point to a possible, I won't say solution, but reduction. I remember when I started in the industry that oftentimes the CP system was a retrofit. So pipeline construction happened, pipe was all buried, everyone was happy there was water flowing through it, and then the CP system was installed subsequent to that. And I wonder if possibly exploring going back to that, precisely because if you've got the full-on construction team, you've got a lot of not just the construction workers, but you've got all the affiliated stuff. You've got the little spaza shops, and you've got the support networks, the transport people, and so on. If the majority of those have left site and you just have your 2 or 3 CP installation people, I wonder if maybe you would find that there is less option because you're not such a draw card. You aren't, so the 3 people working on the line is not a big thing like there's, 50 people and maybe I can get a job kind of approach. It's just a thought.
Well, one of the other things in that regard is to install these chambers or enclosures empty.
Yeah.
So that when they get opened, there's nothing there, and then retrofit. Now, the challenge with that, of course, is that in many parts of the country, when one installs pipelines, you have to have cathodic protection that is installed with the pipeline in order to control stray current interference, which can be catastrophic if you don't deal with it. But there are a lot of pipelines going in areas of the country where we do not have stray currents, and there it is not as important to have active cathodic protection the moment the pipe hits the ground.
But there are so many permutations to this and not necessarily something we'll solve very quickly. Neil, we've spoken about smaller rectifiers, switch mode rectifiers, burying them. Do we have any track record yet about remote monitoring of these buried components, whether, and it may sound, or it's just ignorance on my part, whether you're going to get sufficient signal strength from buried signal generators for a remote monitoring system, whether it be on your rectifier or even just on a buried test post?
Well, I understand that the data transmission aspect of it is such that you can have an aerial or a transmission system built into the lid of the chamber or associated with the lid of the chamber, so that it can, in fact, still transmit and receive signals. So that also goes back to the advances in technology in terms of the power supplies, that where everything is now working digitally and with relatively small power, that you can get sufficient signal through a non-metallic lid as opposed to an old-fashioned cast iron chamber lid, for example, that it enables communication. And that's really all you need. If you've got communication, you can then monitor and control your devices. Yeah.
Yes, you're on a winning wicket. Well, let's hope so. When you said they need an aerial, I'm sorry, I went back to those old bunny ears we used to have for TV, and I just thought that's a draw card if ever these little ears sticking up out of the
Yeah,
ground.
can you imagine every chamber with bunny ears on top? That's an invitation to being interfered with. Yeah.
Neil, just moving slightly away from rectifiers. Historically, in other discussions, we've spoken about the fact that the more modern coatings on pipelines require less current because they are better insulators. And because the cathodic protection of a pipeline is completely current dependent, can we not start looking at using a sacrificial anode type scenario for these pipelines for their CP?
Well, yes, you can, but just before we branch off away from rectifiers, what you said about current demand opens up another possibility. With the older pipelines that had a relatively high current demand, the location of cathodic protection rectifiers was crucial in that you had to have them at certain intervals along the pipeline such that you got adequate distribution. And because you're putting out a lot of current, we had to try and find areas of suitable ground conditions for putting in remote ground beds that would be effective and so on. And with the improvement in the electrical insulation value of coatings, one of the effects of that is that it allows you to place your rectifiers or your current sources further and further apart. And this is nothing new. I remember when I first started in the industry working up in Mozambique, a new relatively small diameter pipeline, it was only 300, had been laid to replace an old coal tar enamel coated line. Part of the line was an extruded polyethylene and polypropylene system. The balance of the line was a multiple tape wrap, line wrapped, with the net result that it had very, very low current demand. And I can remember during the initial commissioning of this line, doing a current drainage test at a distance of about 110 odd kilometers inland from the terminal. And I could see the effect of that 80 kilometers away. I had 80 kilometers of protection from very, very simple, small current drainage test at one point, at one end. That is quite practical if you have got these high insulation value coatings and coatings that don't degrade with time. So in that regard, the polyethylene type coatings are probably the winners in terms of electrical insulation. And I mean, we see buried high voltage cables all the time. That's polyethylene as the insulation. So instead of having to, for example, place the rectifier at, say your pipeline was 100 kilometers long, you would normally place rectifiers, say, at 75 and 25 kilometers, if for example, that was your design, so that you got uniform distribution. If you can put your rectifier at one end, or if you can put it at an intermediate pump station or an intermediate reservoir where you now have got secure environments, you can push the cathodic protection effect much further if you have these high insulation value coatings. One thing you've got to be careful of is those reservoirs generally are at high points, and high points are generally on the top of rocky mountains.
Don't give us good ground beds. No.
And they don't have good ground beds, but you can put the ground bed some distance away with a long cable.
Yes.
Don't do like one contractor did, and they went and blasted a trench out of the top of the mountain and buried the anodes on the top of the mountain in a beautifully prepared trench and got absolutely zero current out of it.
Because of the rock, yes.
Because it was in the middle of rock, yeah. But if you've got suitable ground conditions, you can do it. And I mean, we had a situation on a pipeline a couple of years back where we mentioned it in one of our earlier discussions, where we actually originally designed it as a sacrificial anode system in order to combine the effect of AC mitigation and cathodic protection. And there was no power available along the line. And then we discovered that they stole the sacrificial anode material to make fishing wire. Well, in fixing the problem, we found that the insulation value on that coating was that good that we were able to then protect the line with a single impressed current system located at the one end in a secure pump station environment. And that is certainly something to look at. It doesn't give you nice, beautiful, even distribution necessarily. But at the end of the day, as long as you've got adequate polarization throughout the length of the pipeline, that's all you need to worry about.
I think that just requires a bit of a mindset change from where is the optimal location for the ground bed now becomes where is the safest location for the rectifier with a suitable but perhaps not optimal location for the ground bed.
Yeah.
And I do think we need to make compromises, and I do think we are starting to look for the high security places along pipeline routes. As you said, pump stations, reservoir complexes are likely to have security and may well make safe spaces for traditional rectifiers, not even the berry type.
Correct, yes.
All right, Neil, we jumped to your little detour. I'm now going to bring you back and say, can we use sacrificial anodes to replace traditional impressed current systems in a kind of practical way?
Well, for sure. Again, going back in time, I was involved in many pipeline projects in my early years where the systems were all based on sacrificial anodes. And we had almost like a standard plug-in formula type design. And you installed anodes every 50 meters. And the number of anodes that you put in the ground was related to the diameter of the pipe. And it was very, very Heath Robinson looking back on it now, but it worked. And in those days, we were dealing primarily with bitumen coated pipes, relatively high current density requirements. And we had to use the magnesium sacrificial anodes in order to provide enough current for that system. And it worked great, but its design life was limited. It was like 12 to 15 years, that sort of time period. And then you'd have to go along and
replace them all.
and you'd go along and dig a new trench and put in a new bank of anodes, connect it up and carry on. But the replacement then was periodic. So the maintenance was not continuous every year, but once every 15 years, you had to do a reinstallation.
But we know that we're not very good at that, are we? And if that is a drawback, I mean, the properties of magnesium anodes haven't changed. So they will still self-corrode, they will still be consumed relatively quickly. What about zinc? I've heard pros and cons. What's your thought on using zinc as an alternative?
Well, I think the pro is that zinc has a relatively low, if any, self-corrosion rate. You can rely on something like 90% utilization of the zinc, provided that it stays on the anode, and doesn't fall off. So that certainly is an advantage, and also that its corrosion rate is not that dependent on current density. So the problem with magnesium that you alluded to is that you cannot just simply throw more magnesium in the ground to extend the life, because as you increase the quantity of magnesium, so you reduce the current density on the surface of the magnesium. If you do that, the self-corrosion rate increases. So it goes from something like 55% efficiency down to 15% efficiency.
That's
so
shocking.
you're on a losing wicket. All you're doing is you're burying money, because it's not going to last you any longer.
Yeah.
And unfortunately, there are some designs that I've seen where people put in a theoretical design of 30 years for magnesium and have forgotten to make that correction for the the low current density and the high self-corrosion rate for magnesium. But then with zinc, the challenge with zinc is its driving voltage. It's really low compared to magnesium. I mean, both of them are very low compared to impressed current.
Yes.
So we're talking about driving voltages of 100 to 200 millivolts with zinc,
which is nothing.
which is next to bugger all. But if you look at coatings that only require microamps for protection,
and
then it becomes practical. And if you take one of these modern polyethylene or equivalent based coatings, where your current density, assuming that there's no significant damage during installation, current density is maybe 10 microamps a square meter. Okay,
nothing.
Which is nothing. So then 1 amp, just 1 amp. All right, you need a lot of zinc to give you an amp, but 1 amp will protect 100 kilometers of 300 diameter pipeline.
Yeah.
And that sounds far-fetched, but you know that example that I told you about,
which is exactly that.
Wrapping, I got 80 kilometers out of 2 amps.
Yeah. So it is feasible.
It is feasible. Yes. Yes.
Neil, I have got a lot more questions related to using sacrificial anodes as an alternative to help us in this quest to find a vandalism or more vandalism resistant approach, but we are pretty much out of time. I'd love you to join us tomorrow to conclude this discussion. And so thank you for that. It's been really interesting, and I'm sure that our audience has found the same. But just to our audience, I promised you an update on our quest for CPD points, and I'm thrilled to share that we have just launched a new CPD accredited online course on pipeline survey techniques. And this short course will give you a comprehensive overview of the key survey methods used in the cathodic protection field, like DCVG, SIPs, PCM, combined techniques. It also looks at pipe potential monitoring and remote monitoring, and even briefly addresses ECDA. It's a simple course, it's clear, it's practical. There are video lectures, multiple choice quizzes, and downloadable summary notes. And EXA has awarded us a CPD point or CPD credit for this course. So we've launched this on our Teachable platform now. Now, if you've previously completed our Understanding Ethics course, you can use the same profile to access it. And if you click on the link below, you can get a direct link to it, or you will find a link via our website and our LinkedIn pages. So we hope you'll take a look at that and continue learning with us. Thank you for joining us, and stay curious.